The next speaker is Jan Forbrich, Radioactivity Reloaded, Young Stellar Objects as Seen by VLBA, VLA, and ALMA. Thank you.
Okay, thank you.
11 plus 4.
Excellent. Is the microphone on? That seems to work. Yeah, after this excellent talk, there's actually not much need for me to reload radioactivity. So the stage is nicely set for this talk. I will focus a little bit more on young stellar objects, and I will show what can be done now with radio facilities. My name is Jan Forbrich, and I'm at the University of Hertfordshire, which is actually very close to London. I get this question very often. Let's try this. A little bit of background. One thing that many people are not really aware of is that there's a lot happening in radio astronomy right now. Several observatories have been upgraded. The VLA and the VLBA have much improved capabilities compared to 5-10 years ago, so something that is not really very visible. ALMA has come online. There's really an unprecedented coverage of wavelength at unprecedented sensitivity, mainly due to broadband receivers and correlator technology. And of course, there's more coming up with the NGVLA idea and the SKA. What does this mean for young stellar objects in particular? If we zoom into a prototypical young stellar object, we have lots of processes happening on the innermost scales. We have outflows. There's a lot of ionized material, thermal radio emission. And if we zoom into the innermost areas, that's really where coronal structures are located, and we have thermal X-ray emission and non-thermal radio emission, both in the centimeter and the millimeter range. So there's really a lot happening there. This is what we would be looking at. One aspect I would like to focus on in particular here, just in this short talk, is what about radio flares? And this is really something, Meredith has shown this spectacular example. This is really something that we know very little about. X-ray flares of active stars and young stellar objects by now are very well characterized. And the radio range, we still know very few of them. On the left-hand side here, I have a radio flare that we published 10 years ago. This is a very deeply embedded object in the Orion Nebula cluster, an object that was basically not detected and then became the brightest source in the nebula. This then disappeared. We haven't really seen it since, and many other observations. So the question really comes up, how often do these happen? This is an order of magnitude event. What's the importance? What's the context with X-ray flares? Do they occur in tandem? And of course, one way to figure this out really is to go back to Orion. We started a large project to study young stellar objects in Orion. The advantage is you get many, many objects in the same beam, so you can really cover a lot of ground in terms of total time coverage. We started with the deep VLA observation to get a deep catalog of radio stars in Orion. This increased the number of sources by more than 7 over the previously known sources. And then we looked at all of them in the time domain. And in particular, in this case, also with simultaneous Chandra observations. We looked at a couple of surrounding fields. And in one feature of the VLBA that is new and that is also very cool, we can follow up all of them with the VLBA due to advances in correlator technology. So we also have VLBA information for more than 500 sources in Orion. This is an ongoing experiment. And we're expanding this into the millimeter range with ALMA in the inner cluster. And so in the remaining minutes of this talk, I will highlight a couple of features of all of these data sets. One thing that is really new on the radio side is we have much, much better radio images now. I deliberately did not put any labels here. One of these images is the HST optical view of the inner ONC, and the other is our radio image. So there's a lot of structure that is really now nicely imaged on the radio side. You might have guessed that the left-hand image is the Hubble image because it has the trapezium as nice bright stars, and on the right-hand side is the radio image. So propelets, lots of structure in the inner nebula are actually nicely imaged. What happens now if we slice up this deep observation in the time domain? What we have to do is really we have to image time intervals in the entire cluster to get the imaging right, and we can do this in different time intervals. And it turns out that there's a lot happening. This looks a little bit like an eye exam, but I will try to go over these plots individually. This is for two different objects, just as an example. We have the time on the x-axis, imaging these data sets at different time intervals. So we have entire epochs, we have 30 minutes, and we have 6 minutes on the right-hand side. And you can really see, if you compare the flux density of the concatenated data set for these sources, it's the blue line in the first plot, that things look completely different at higher time resolution. And in particular, in these two cases, we see these nice flares arise on short time scales that are sitting in this deep data set. And if you just image this without paying any attention to the time domain, it really has all kinds of technical consequences on how you interpret the data as a whole. So there is this variability going on. And of course, one question is going back to this one flare that we published 10 years ago. How often do we see an order of magnitude variability if we can suddenly look at hundreds of sources in Orion in one go? And the answer is that there's actually quite a lot happening. This is a plot for all sources on the x-axis. This is by source number. This is any pair of images that have more than a factor of 10 variability. There's more information encoded here on timescales. But the point really is that there's a dozen or so sources that show order of magnitude variability, even in this one observation. So it's really something that is not so unique that you wouldn't see it in an observation like this at all. So there's really something happening. Very briefly, what's the context with X-ray observations? These are the same two radio flares that I showed earlier in the upper two panels. And the simultaneous X-ray data in the lower two panels. There's a lot of information. Again, here we have the binned light curves in black and median photon energies in red. And the blue confidence intervals are adaptively smoothed versions of these light curves. And it turns out that there is a lot of complexity in this comparison of radio to X-ray data. On the left-hand side, we see that this relatively small radio flare up there where the source was not detected on all other occasions actually has an X-ray feature at the same time, even though it's not very bright. And on the right-hand side, we actually have a direct match of this very bright radio flare with an increase in X-ray emission. But there's a lot more happening. If you look at the first epoch, the X-ray activity is already as much as in the second epoch, but the source is not detected in the radio. So if you know more about this, we would be very interested also in learning more about the phenomena that could be at play. Very briefly, toward the end, what can we do with the VLBA and ALMA here? This is an ongoing program with the VLBA. We suddenly have a factor of 300 better angular resolution. One can think of looking at, so this is at a range where one can maybe even see large magnetic structures connecting the star to the disk. That's a bit of a stretch, but it's getting there. We do have absolute astrometry. It's the closest thing we have to a direct absolute astrometric measurement. There are some interesting offsets with Gaia. This is this plot on the right with offsets in milliarc seconds in the astrometry, which is interesting. This could be due to multiple systems and also an astrometric cross-check with Gaia. And the goal really is to, in the end, have proper motions in the same way as we have it for Gaia, but for the embedded objects. Okay, and toward the end, very briefly, this was nicely introduced by Mary. This already we can also look at the millimeter range and look at synchrotron emission. This is something that we first did for a T-Tori binary system also a little more than 10 years ago. And I would like to show you some first data here that we just got of the inner cluster of the inner ONC at 3 millimeter in the continuum. This is centered more or less on the BN object. Lots of young stellar objects detected here, and we do see several kinds of variability and flaring going on. That's I won't have time to show much of that right now, but this is really an interesting extension of this to the millimeter wavelength. And I will leave you with my summary. Thanks for your attention.
Thank you. We have time for questions. Oh, sorry. Over here, please. Is there somebody helping? And then you, yes. Could you, for him next. Thank you.
Marina Kunkel, Western Washington University. How widely placed is your VLBA astrometry in the time domain? You said that you have 4 epochs. What is the time baseline between them?
So this is ongoing, and currently it's 2 years. But it will be more than 2 years eventually.
So have you tried getting the parallaxes from them?
At the moment, it's not enough by itself to fit parallax information.
Okay.
Yeah.
Yes.
Klaus Strassmeier, hey.
Oh, sorry. Question.
ARP Potsdam. You had this beautiful picture from Feigels in the Mommerly review on there. Mm-hmm. Could you actually indicate there where you think the millimeter radiation comes from? Is that completely disk related, or is it?
Oops,
yeah.
There we go.
Right.
So there are probably several different origins for the millimeter emission. If we think of the synchrotron part of high energy processes, then it's probably really from the innermost corona. And but additionally, there is emission also from the disk, of course, in the same range, from a different emission mechanism. So that we could see thermal emission on larger scales, but the non-thermal emission would really be from the innermost areas.
Question over here.
In your joint radio and X-ray data, do you see any examples of the Newport effect, which for others is where the X-ray slope rises and the slope is proportional to the radio flux?
So this is indeed something that we've been looking for. It's there's surprisingly not really any clear example of it. So there's either a direct match without a significant change in time, so it's really simultaneous, or it's completely different. So there's no clean example of it, even though that obviously doesn't rule out that the effect does play a role also in these objects.
Okay. Anything else? Let's thank our speaker again. Right. My mouse.